Hello and welcome to another episode. As you may have noticed, this is episode 1.5. The reason is that episode number 2 about phone intros is scheduled for the weekends, but I really wanted to elaborate more on one very simple and useful data structure that we looked on in the previous episode, the Fenwick tree. Now, the way I encourage you to think about the Fenwick tree in particular and about pretty much every data structure is by memorizing the operations they perform. That's it, the interface. In this context, one can view Fenwick tree as a cheaper version of the segment tree. Basic Fenwick tree allows range, sum queries and point and date queries, but we will also cover some variations. Now, let me explain what are the operations, right? Let me pull the demonstration. All right, so imagine we have an array of several numbers. Let's say 1, 2, 3, 4, and 5. And the queries of two types come to us. Now the first query gives us two indices, left and right, and asks about the sum of elements. That's it. We want to return sum of array entries from I equals L to I equals R, from left to right. So for example, we can get something like 0, 4, or which will mean basically that we need to return the sum of the entire array, right? So this is element with index 0, and this is element with index 4. But we also may get some different queries. Like for example, somebody may ask, what is the sum of this interval, right? By providing indices 2 and 3. So this is the first type of queries. It is range sum queries. So we are interested in the sum on some range. Pretty reasonable name. Now the second type of queries is point on date queries. In these queries, we are given two integers, some index I and some value v, and we want to assign the value of v to the element with index I, right? So we can change our array little by little over the time, and we also may ask what is the new sum after this operation on some interval, right? Now we have a problem. I have translated a very good preparation material by St. Petersburg State University. It's back from 2013-2014 season, and it's pretty good. I mean, you can still solve it in some kind of gym on Codeforces. Keep in mind that all the gyms on Codeforces are pretty slow. Pretty slow in testing. So you may need a couple of minutes while your submission waits in the queue, because back in the day, Olympiad questions, they had input files, right? So you literally had to read input from file. Nowadays at Codeforces, you can just read from standard input, which is, in my opinion, much more convenient. On LeetCode, for example, you don't need to read input at all. So because of this issue, server needs to go somewhere, grab that input file, and it's pretty slow. But if you want to test your solutions after today's lecture, you're welcome to do it. I'll put the link to Codeforces gym in the description, and I will also put the link to the statements, basically, so to the translated statements, because original statements are in Russian and there's no English version. So I translated one for you so that you can understand at least what's going on, right? Not everyone knows Russian. So this problem will be just ASQ, so range sum query, basically what we already covered. And this is exactly what basic Fenwick tree data structure solves. Now, I will need a little bit of image here to explain how Fenwick tree actually works. So let me grab some numbers, let's say from 0 to 7, right? Not necessarily these numbers, I just take some to make it clear. So these are the indices, right? Now, Fenwick tree is an array of the same size, but it doesn't store the array elements. Instead, it stores the sums on some segments, right? So, for example, at entry 0 and every second entry, it stores just that. So we really need some sort of table here. So let me quickly draw one. I believe we need 4 rows, but let's make a little bit more just in case. Okay, so yeah, I'm just trying to draw the lines of the exact necessary lengths. You will see why in a second. Just like. Okay, so we store the following elements. And I believe I terribly did it wrong. Right. Now it should be okay. So in the entries of the tree with all the odd, I mean, every first entry, but it's all the even indices, we store just that value, okay? So here we will always have the first element of the array. Here we will always have the third, that's it, the one with index 2, and so on. Now things get interesting. So instead of doing just that, we do the following. On the second layer, we store the sums on the segments of length 2. So we will keep growing exponentially with base 2. You can already see where this is going, right? Because as you may know, the complexity of the Fenwick tree per operation is log n, and I believe everyone can see that the depth of this kind of structure is also log n. So what does it mean is that in the entry with index 1 of the Fenwick tree, we'll keep the sum of the first and second elements. So these two. So 3 at 1 will get array at 0 plus array at 1. And the same thing goes for 3 at 5. 3 at 5 will get array at 4 plus array at 5. On the next level, right, we have even longer segments. So the entry with index 3 of the tree will contain the sum of first 4 elements. That's it, array 0 to array 3. Then we go even higher, take by 8, by 16, by the powers of 2, basically. Now, what this allows this kind of structure has some really nice properties. In particular, every prefix segment can be, you can write any segment of the kind from 0 to somewhere, like from 0 to R. You can write as, I should write union of several segments, right? So I'm not going to write anything exact, just from left I to I, where I goes from something. And interestingly, I goes only to log n, where n is the size of the array. So for example, if we were to have like 1 million elements long Fenwick tree, then log n would be just 20. Pretty efficient. Now what this allows, as you may expect, is that if we can represent a segment as a union of several segments and want to compute the sum, right, of this segment, then we can just compute the sum of all of these segments. And each sum of this segment is already computed because we just say that fifth entry of the Fenwick tree contains the sum of fourths and fifths of the original array. So pretty nice property. I mean, it's kind of obvious visually, right? If you have like, even number, then you take 1 and out of it, right? So let's construct this decomposition from right to left, starting at 6. So we want 0 to 6. We take a look at the last element. It says, I only know my sum. I don't know any more segments, right? I only know this. So I will give you this, right? From 6 to 6, basically. But he says like, okay, go ask the previous element, what is his segment, or their segment, I should say. And the element with index 5 says, okay, my segment is from 4 to 5. I can give you the sum on this segment, right? So we add another segment into our decomposition. Now, for say 5 already told us the sum including to 4, right? So there is no need to ask 4. Instead, we go to the previous value and ask 3. And 3 says, oh, okay, I have a pretty decent segment for you. I have a segment that goes all the way from 0 to 3. And this is what you want. Like, you already got your decomposition and it contains only 3 elements. And this is pretty expected because this array has actually has 8 elements, right? So log base 2 of 8 is 3. We got decomposition into 3 segments. Perfect. Makes perfect sense to me. Now you may notice that I only talk about queries, or should I say segments of the form from 0 to R, right? But original problem contained queries from L to R, so from left to right, not necessarily from the very beginning of the array. Now, there's one simple way to overcome this issue. Let's say it by noting that segment from L to R is the difference of segment from 0 to R and segment from 0 to L minus 1. And you got to be careful about whether or not L actually equals 0. So be careful just to subtract only when you need to subtract, right? So there is no this moment if L equals 0, because it wouldn't make sense to have a wrong interval which goes from 0 to minus 1. This is not how the intervals work. So in case L is not 0, you got that pretty decomposition as a difference. Now, when you want to compute the sum, you just compute the sum from 0 to R, from 0 to L minus 1, subtract them, and you get your sum, right? Pretty simple. Okay, so we already know how to answer the range sum queries. Wouldn't be a big deal if we had no update queries, but update queries are also pretty fast, right? Suppose that we want to update value at index 2, which sums, which entries of the tree we should change. Every single one that has 2 in them, right? But 2 can only belong to log n such segments. Why? Because the depth, right? The depth is not big. It's not big enough to contain many more entries of 2. The depth is log base 2 of n, or I can just write log n, right? So element with index 2 belongs to tree at index 2. This is tree at index 2. Tree at index 3, this one, and tree at index 7. Only 3 elements. Now, of course, these are asymptotical bounds. Okay, so 0 is contained into log n plus 1 entries, but nobody cares about plus 1. So, right? Asymptotically, the complexity of update is to change log n elements. That's all about the Fenwick tree. Now, it may sound very tricky because it is not obvious, far from obvious, how to obtain indices 2, 3, and 7 from 2. So how do you know, like without drawing this picture, how do we know to which entries of the tree element with index 2 of the original array belongs? Now there's one pretty decent trick with bitwise operations that allows very simple enumeration of these positions. So given an index, you can easily iterate through all this just by going. Every next one can be obtained from the previous by some tricky bitwise operation, and we will look at the exact count in seconds. And at the same time, like I was saying, how to obtain representation like that. It's also not obvious. I actually said that we like kind of ask the current entry of the tree. What can you tell me? It tells you something, and then you go to the first location that you still don't know. And this tells you that, and you go to the first location that you don't know, right? And there's also a convenient way to enumerate all these positions as well. And we are going to look at this way right now. Let me pull some code. Now, today, as you may clearly see, we are not going to write code live because there were several issues. Now, first of all, I started recording and typing this code. But then when I tried to submit to Codeforces, I figured out that Codeforces, all gyms are very slow. So there was absolutely no way we can wait 10 minutes until each of our 4 questions gets tested. Yeah, so I just thought, let me write everything in advance. All this code will be published on GitHub, and the link will be in the description. So if you want to grab it for yourself, you can totally do. And it's not the most the most competitive style code, let's put it this way. It is really more about showing nice practices on the interview. As you can see, I have a class for Fenwick tree. It's absolutely not necessary. You can just have a plain array and then several functions operating on that array. But like basic object-oriented programming principles says that if you have some data and some operations which modify and probably not modify, but query this data, it should be encapsulated in one data structure, so in one class. And we have exactly that. And we also have like several minor style guide points here, but nothing you really have to worry about. So notice how we, like looking at this interface, right? If I were to now name some method range sum, right? It would be pretty obvious what this data structure does. Okay. It can assign a value at index, it can return sum from left to right, it can initialize with some array. It can also, like these two are helpers, right? So I just told that sum from left to right is obtained like difference from 0 to right, and this helper method returns just this. So this is sum from 0 to right, and increment is another helpful method for assign. So I also have a template version because sometimes values get too long integers and I don't want to write int 6040 everywhere. So I just make this class a template and then I can just write int 6040 once, which is another cool feature of object-oriented programming and C++ template. You can just say once what you want, and then all the operations will be converted. Like if you want maybe to save some memory, you are pretty confident that your Fenwick tree operates with entries that are, say, up to 50,000, right? Then you can use something like int16t, right? So you cut the memory usage 4 times, just like that. With changing only one parameter, there is no need to retype int16t everywhere in the code. Here is potentially the biggest memory usage when we have a vector of long integers. So yeah, templates and enclosing your data structures into interfaces classes is really good because, and also C++ allows obviously separating the implementation from the interface. So you can just look at that interface and you immediately realize what it is doing. It is very simple to memorize this interface. Like I would do that on LeetCode, but it just takes so long. So that's why I don't really do it when I'm limited on time. But today I had a lot of time to write to solve these 4 problems. So I decided, so let's do my best. Let's try to do my best. Now, first problem asks about just range sum queries and point updates, so nothing smart here. We open the files, and in case you are interested in working with files, you can just free open as standard input and work with your SPDC all the time afterwards. I'm not going to cover much of the input and output. I believe you're familiar with it. Yeah, if you ever used Codeforces or some other competitive programming environment that is not as user-friendly as LeetCode, let's put it this way, then you're familiar with C++ input and output streams, right? So once we read all the elements of our array and initialize the Fenwick tree, we can start processing queries, and this will be it. So main code is very simple, and all the query processing is here. Just a couple of lines. With that in mind, let's head into actual implementation of the Fenwick tree. So initialize, there's nothing smart here. We just do a batch of assignments, right? So we just assign, we actually start with array of zeros and with an increment index the entry at index by the corresponding value. Now I know that this method of initialization takes n log n operations. Basically, it's not great because it is possible to do initialization of the Fenwick tree in linear time and also in linear time with constant memory. But let's be real. So first and first, nobody cares about constant memory. And second thing, in practice, if you have not that many queries, right? If you have a lot of queries, then reducing the complexity of initialization won't reduce the overall complexity, because overall complexity will be determined by sum and assigned queries, right? So there's really no point in speeding up initialization, which you do once if you have a lot of queries, which you do all the time. Now, if you, however, have not that many queries, then just more efficient data structures exist. Right? I believe that something like square root decomposition, if you have at most square root of length of your array queries, then square root decomposition works faster than Fenwick tree. And I'm not sure that we will talk about square root decomposition in nearest future, but if you're interested, let me know in the comments. We totally can do a video on that. We have some problems to solve on Codeforces. And yeah, the reason why I take Codeforces problems, because usually they are just nicer to work with. I mean, they are more competitive style. They totally can appear, like some well-known competitive problems may appear at the high-level interviews. So you definitely need to be ready for that. And they are sometimes less about implementation and more about ideas, which I really like. I really like algorithms, like inventing algorithms. I'm not really good at it, but yeah, it's better than just writing, like, I don't know, same dynamic programming short time in one day. Okay, so we already covered initialization, which is just a couple of manual increments. Sum from left to right is just a difference. Assignment works through increment. So the two interesting methods here are sum from 0 to right, which goes as follows. So we start at index right until right is at least 0. We ask right, so we ask the element which I was just showing, right? Let me pull the image back. So what happens here is we just go to tree at index right and ask what sum can you show to me, right? Just like we were doing here. For example, right equals 6. It says, well, I know that my sum is A6. I will return A6 to you. We say, okay, we will add it to our accumulator, let's say. Then we have a pretty tricky increment condition, which actually like right bitwise and right plus one tells us we give the right end of the segment, right? And it gives the left. So for 6, I believe we can figure it out. Let me write something here, actually. So what is 6 in binary? 1, 1, 0. Now what is 7 in binary? 7, right? 1, 1, 1. Now we take bitwise AND. It results in 1, 1, 0. So we get 6. So this statement here, you give right end of the segment and you get the left end. Let's try this 5, right? Just to see that we really get 4. So we take 5, we take a 5 plus 1, we take bitwise AND, and you can see that we get 4. So you give right border of the segment and you get the left border. And when you get -1, you say like, okay, I know I processed this entire segment. Let me go to the previous element and ask it about its sum. So there is just nothing really complicated. You just figure these indices. You given right, you get left because of bitwise operation. There are different ways of visualizing the Fenwick tree in which this identity becomes trivial, but I believe that it is already clear enough. So you just know that this statement gives you left end of the segment based on the right end, right? And you keep going until you hit 0. And this is 0, like now we have 3. 3 is what? 0, 1, 1. You add 1, you get 4. You take bitwise AND, you can see we get 0. You subtract 1, you get -1. And obviously, you don't want to ask a non-existent element of the tree about what is your sum, right? Because it's just the memories that you do not control. It is really bad, so you don't ask, you just break based on this condition. Okay, so the update query is pretty much the same, like one-to-one correspondence, except that you take bitwise OR, not AND. So you're given some index 2, you say, okay, index 2 is valid, let me increment the corresponding entry of the tree. Okay, you take what is 2 in binary, 0, 1, 0. You add 1, what is this? It's 3. You take bitwise XOR, right? I don't really know, this looks a bit silly. So I will write XOR this. So or bitwise or is 3. So you get to 3. It says, okay, let me increment the entry in 3 at index 3. Now I take 3, add 1, I get 4. When I take bitwise OR, I get 7. So I just go the other way around. Just go to the next segment, right? This is it. You may think about this in the following ways, that there is, like, why is it called tree? Have you noticed that all we were working so far, is just an array? And I said explicitly that you can do not include include do not encapsulate everything in a class. You can just work with pure array. Everything will be fine. Now the reason why is this is called tree, because you can look at this kind of structure, I believe. It is like this. And it's really tree. So every segment has its parent. The parent is the first one below, who is colored, right? It's a pretty simple structure. It's not a binary tree. Is actually here at the very root, you will have log n children of this root. But you don't really care about this tree structure. You just know that you can traverse its edges based on these simple bitwise operations. Let's put it this way. And that's it. That's entire implementation of Fenwick tree. If you remember what we were doing last time, you can really simplify everything if you don't rewrite templates, if you do not create extra methods, you just work with pure array. So this code is definitely not the shortest one, but the upside that you have a convenient class that you can grab and copy paste into your, I don't know, lead code submission. Obviously, this won't work on the interview. So I really encourage you to memorize these two operations. They are pretty simple, and it's really great that they are dual, right? Here you take bitwise and here you take bitwise for. You memorize one of them and the other will come naturally. Here, there's nothing to memorize. You just know how the data structure operates. From left to right is the difference. You assign the correct value. You increment by the correct value. Initialize is just a bunch of increments. So yeah, this is the entire code for our first problem. Our first problem was just French sum query. You are welcome to test your solutions in the Codeforces gym. I will put the link down in the description. This solution gets accepted in I don't know how many milliseconds. I believe it's pretty fast. I mean, it obviously can be, you can speed this up by writing just integers where you can, but I don't want to think about it. I don't want to run into any kind of overflows. Now, of course, if you write in Python, you don't have to care about overflows, but remember that it comes at the expense, right? Your integers are actually higher. I mean, they take more memory. So I mean, in C++, I believe that you can have around 2 times more memory allocated, more elements allocated than in Python. Especially if you allocate like a vector of vectors, because overhead for Python list is just non-variable. Okay, I believe this is all for problem A, because it just implements data structure. Now the things get interesting. One of the reasons why I really like Fenwick tree is because it generalizes pretty easily to higher dimensions. So we can have Fenwick tree in three-dimensional Euclidean space, and it will be pretty much the same. Like if you take a look at the operation, then you have the same loop with the same binary operation just 3 times, right? So yeah, I believe this is the easiest three-dimensional data structure I know, and probably one out of 3 that I can write. I mean, I can write by memory. Okay. I believe some sort of segment tree I will also be able to write, but definitely not as easy as that. I mean, this is as simple as 3D data structures get. You cannot go much simpler. And the reason why we need a three-dimensional data structure is because our problem is concerned with three-dimensional cube, n by n by n cube. We have 2 children, Vasa and Beta. You can change the names to whatever you like to. I just decided to stick to the original statement. So yeah, I don't know. Anna and Bob, like Anne and Bob, right? Good names. So one of them is watching the sky, namely the n by n cube. 2 events happen. First, some stars may appear or disappear in some of the 1 by 1 cubes. So let's say like he looked at this cube and he noticed that some stars have appeared, some have disappeared, some have moved, maybe to the next cube, something like that. And the second event that can happen is that his friend comes by and asks how many stars are visible in some cuboid. Cuboid is not really a cube, it's something very similar to a cube in the following meaning. Like you have all the angles are right, so 90 degrees, but sides don't have to be equal. Okay. So you have something like this. Maybe it is 2 by 2, 2 by 2 by 5, right? Maybe this one is a little bit shorter. And this is 2 by 3 by 7. I don't know. Something like that. Okay. Now, obviously, this cuboid fits entirely into the cube that first is watching. So there's front face of this cube and it goes all the way out of the screen. So it's pretty decent cube, okay? But not all that big. Its sides are limited by 128, and there are several reasons for that exact value. So first of all, the Fenwick tree is really concerned with the binary lengths of your numbers. As you can see, binary operations are everywhere. So it is really convenient to have the power of 2 here. And second reason is that you cannot get it higher, right? And because you will have n cubed cubes. 128 to the cube is already 1 million. You should take, I believe, a little bit more than 1 million, whichever. If you take 255, right, 56, then you get something like 9 millions. Well, probably 8, but I believe that 55, 56 also matters. Sorry, I just constantly forget that they index starting at 1. So yeah, that's why you hear 225 instead of 226 or 56, whatever. So this cube is too big to process like by hand. I mean, like to manually compute the sum every time we are asked for this. And this is the reason why we need Fenwick tree. So increments and sums are pretty simple. Now this one computes the sum in the cuboid starting at 0, 0, 0 and going all the way to x right, y right, z right. So this cuboid has one common vertex with the big cube. It poses some limitations, but these limitations are not exactly unbearable. Let me demonstrate what I mean by that. So let us go back 4 minutes, just 4 minutes, to two-dimensional space, because I know that three-dimensional space can be hard. So we know that we can answer like any query of this kind, which starts at the left upper corner, left top corner, right? Suppose, however, that we want to answer something like this, right? Let me use a nicer color here. So how do we do it? Now, the first instinct is to take this, right? It's the best that we can get. Okay, but we have taken several things too many times. Like this should be discarded, this should be discarded. Not a big deal. We can subtract them, just like we subtracted in one-dimensional case. We subtract this, and we subtract this. Now you may think that that's all, but not exactly. Like we are almost done. Okay, and the reason why we are not exactly done is because we added this region only once, but we subtracted it twice. So basic inclusion-exclusion principle gets in our way, and we need to add it back, right? We added it once, then we subtracted it, and then we subtracted it again. So we kind of borrowed it, and now we should put it back. Right? We have to. We absolutely have to. And the same logic applies in three-dimensional space, with the only difference being that we take one big cuboid, we subtract 3 of them, then we need to add 3 more back, and then we need to finally subtract the final one. So it's just inclusion exclusion. You can I don't know, take your Rubik's Cube in case you have one. I'm a big fan, as you can tell by my background. I have 3.5 cubes with the intention of having 3.5 episodes per week. Let's see how it goes. I hope it's possible. So yeah, just try to draw some pictures. You will understand why the formula is just like this. It's just taking the best approximation you can, then subtracting necessary things, then looking for the parts that you subtracted too many times, adding them back, and then subtracting again. So I believe this was all for this problem. I don't really know any other ways to solve it. So it's pretty standard problem. Stores, right? I don't know, like pretty much every algorithm course in any sort of Russian university, like ITMO, I believe, St. Petersburg State University, obviously, Moscow National University, Moscow State University, right? They all have this problem somewhere in their 1 year long algorithm course. Now, in case you're wondering, I do not study in Russian. I just have a couple of friends there. And yeah, we chat about what is going on, what courses do they have, what courses do I have, something like that. Yeah, so I believe this was all for this problem. If you have any questions, like, for example, why do we need CSTD EO here? Because we want to reopen, right? Reopen file as a string, as standard input, or anything like that. So it's completely fine. Like, you may ask, what the hell is this? Why don't you write everything in the same line? Because it gets too long for you to see. Now, yeah, you can put a backslash and just, it means the line break. I believe this is actually the correct way to break lines according to the style guide, to the Google C++ style guide. Tell me if I'm wrong, I haven't read it in a while. If you have a question like to implement this entire data structure in Python, I believe I will give you some hints, but I just don't have time to write this in every programming language. In Java and C#, I believe this will be more or less the same modulo like std vector. You will have some other sort of array, I believe, in Java. Yeah, that's pretty much it for this problem. And this is the only way to solve it. So if you don't know Fenwick tree and you face this problem, you're done. There's no other way to solve it. Or maybe I'm a total moron, and you'll tell me another way, and I will tell it to all my students next time I see them. Okay. Right. We have two more problems, very interesting problem. Now, problem C is fairly well known. I believe there are different ways to do it, so you're not dead if you don't know Fenwick tree, but still, it's a pretty decent way of solving this problem. It has linear complexity. I'm pretty sure that you can have just standard data structures and solve it in analog n time, but this is not something we are here for, right? So the problem is as follows. You're given an array of n integers, and you want to find the number of inversions. Now, inversion is the pair of indexes. Let me pull some example. For instance, if we have an array 1, 2, 4, 5, there are no inversions, because an inversion is a pair of indices I and j greater than I, such that array at I is greater than array at j. So it's a pair of entries in the array that are in the wrong order, right? If you sort them, they have to swap. And this array has no inversion because it's sorted as it gets. If, however, we had something like 5, 4, 2, 1, then every pair is inversion. It's in the wrong order. It should be increasing, but it's decreasing, right? So there are 6 inversions here and 0 inversions here. And this is exactly what sample test cases tell us. Yeah. So how do we solve this problem? Now, first, we need some sort of preparation. And this preparation is converting our array to a permutation. It's a technical detail. Let's assume that you can do it, like you can convert, I don't know, 1, 7, 3, 4. You can say, okay, 1 is the smallest number. Let me place 1 here. Right? 3 is the second smallest number, so let me place 2. 4 is the third smallest, so I'll get that. Now, the reason why we need this is because our initial entries can be huge. There are basically no limits. I believe the limit is 10 to the 9th, but it's not written in the question. So I have not written it as well. I mean, it is not written in the original question. I believe it's 10 to the 9th. So everything that fits in it can be 0. It's really uncomfortable to work with that huge values, so we convert everything into a permutation because now, and I believe that this kind of trick is called something like coordinates compression. Let me just write it down. It's a pretty useful technique. You can often convert the problem into the version in which you can employ simpler data structures. For example, if you want to have a frequency counter and your elements are up to 10 to the 9th, then your only choice is to have an ordered map, right? So hash table. Now, there's nothing particularly wrong with hash tables except for the constant hidden in the asymptotics, right? In the big O notation. I believe the constant is pretty decent nowadays compared to what it was like 5 years ago, but it still can be at 20. So your kind of linear unordered map gets to kind of and again unordered map, which is not good. Well, life is hard. That's all I can say. So, but if you instead use coordinates compression, like obviously it takes some time, it requires sorting these entries, like to know which element gets which index. But after you do it, you can instead use array and use values as indexes, right? And array has pretty low hidden constant in it. If you do not reallocate, then hidden constant is 1. Right? If you reallocate, then probably it's like 3. I don't know, reallocate when extending, reallocate when deleting. Yeah, it's probably it is 3. Okay. Still much better than Python. So this is a useful trick, not only in this problem, but in general. Now, what does it allow us? Here it allows very interesting approach. Let me highlight the other part of the code. Now, what we do here, we create an inversion counter, which will just be our accumulator. And now we do very small thing. So it is just real small. We look at our elements one at a time. So initially, our Fenwick tree is all zeros, right? 0, 0, 0, 0. And let me just assume that there was some kind of 0 here as well, because I forgot that in my solution, this should be zero-based indices. Okay. So what you do is you take a look at 1. How do you know how many conversions there are? Like, you can look at this part of the Fenwick tree, or should I say at this part. So once we see entry 1, we are going to change this element to 1, right? With that in mind, like when in the future, when we will see entry 0, and we look at 0, like inversions are numbers that are greater than 0, but the ones that were before 0. So this will be all the numbers to the right. Let me do a couple more iterations just to show how it evolves. So we look at 1. Previously, there were no elements greater than 1. So we do not have any inversions before one, right? Then we look at 4. Previously, there were no entries bigger than 4 because, and there will be no entries bigger than 4 because 4 is the maximum. So again, like here, there is nothing. So we don't have any inversions from 4 going backwards. Now, when we see 2, we say, okay, like 2 will go here. But if we query our data structure for the range sum on this interval, then we will see that there was one number which is before 2, but greater than 2. So there is one inversion from 2 going back, and this is exactly to 4, right? So let me highlight what query do we do to our data structure. And this one, this detects this inversion. Now we keep going. We see 2, we add 1 at position number 2. We see 3. We again query for elements bigger than 3. We get 1. This is another inversion, right? We keep going. Now we see 0. And we ask about elements that were greater than 0, but came before 0. And it's every element. So when we ask for the sum on this interval, we get 4 as an answer. And this is because there are 4 inversions from 0 going backwards. So just like that, we showed how to transform our problem into the operation supported by the Fenwick tree. Pretty decent result, I think. I mean, we got, if we ignore the sorting part, then our complexity is linear. No, wait, I'm stupid. Increments are log n each, so it's still n log n. All right. Still a good solution given that n is only 50,000, right? So n log n fits perfectly into 2 seconds time limit. Yeah, in case you are interested on Codeforces, I don't know what you can do today, but back in the day, I believe that 10 to the 5th, like 10 to the 6th, meant that something linear is expected. 10 to the 5th corresponded to n log n. And yeah, these are the basic asymptotics you have to know. Something like 1000 would be quadratic. And I believe you can derive all these bounds if you assume that you have a total of 10 to the 8th to 10 to the 9th operations. But for these years, it's more like 10 to the, it's somewhere between these two values. I believe that nowadays Codeforces can handle like 2 times 10 to the 9th operations at least. Codeforces servers have evolved. Not sure about code servers, but whatever. Yes, just like that, we count inversions. Let me know in the comments if you have any questions regarding this problem. Maybe I will try to answer your questions in the comments. And notice that the interface has changed a little bit, but this is only because I got rid of unnecessary methods. So if you remember A's problem, What do we have? We have explicit constructor. We don't have initialize because our initial state is zeros. And we don't have assignments because we do not assign, we only increment. Right? When we had assignments, we needed to remember what is the current value to know by how much it actually increments the assignments, right? So this, like, if you make all the methods public and you don't get rid of unnecessary ones, then you can just take this interface wherever you go, like whenever it is online assessment, I believe you can. You sort of can use it I mean, if you have a Blackboard interview or something like that, then you can just say, let's use Fenwick tree. It supports such and such operations in such and such complexity. And in case you are asked to write it, the only thing you have to remember is binary tree. So you will be able to do it like 100% of the time. Like 10 interviews out of 10, when asked about Fenwick tree, I will be able to come up with this, and you will be able to come up with this as well. So if you write this interface several times, implement it, then you're pretty memorize it. So pretty guaranteed, let's say. Yeah, and the last problem for today that I wanted to discuss is segment update. Now, Fenwick tree is fascinating in that regard that it can handle segment updates, but only if you have point queries. So you have two cases. First is segment queries. So you're given a segment and you want to query the sum. And point updates. So segment queries, point updates. And the other option is point queries and segment updates. And this can be done via very smart trick. Very smart trick. Let me bring. Okay, I will take like the initial state of all zeros. It's not very different if the initial state is not all zeros. So if the initial state is all zeros, and suppose somebody asks you to add 1 to this range. So they really want you to make, let's say even to this range. So they want you to change 4 elements. No, you say, I'm smarter than that. I don't want to change all of n elements all the time. I will only change first to +1, and then I will change the first past last to -1. Now this is a really genius trick. I mean, I don't remember who showed it to me. It was probably some standard algorithms lecture, but man, this is smart. Like, the thing is that current value at index I is not contained in the entry number I. It is the prefix sum of first I elements. And as we know, Fenwick tree is pretty decent in computing prefix sums. So yeah. Yeah, let's see how it works. So the true state, let me make it like this. So we will have like Fenwick tree state. So here we have a Fenwick tree state. It's the current state, current state of the Fenwick tree. And here we have actual array state. So the actual array state should be different, but we don't care because we are smarter than that. So the actual array state is like this. Suppose that we are given some more range of date queries. So suppose that somebody wants us to, we increment that query, that range. Suppose that somebody wants us to decrease this range by 2. So the actual array state will be -2, -1, -1, 1, 1, 0. Now what do we do instead? We indeed decrease the first element of the range by 2 and update, add +2 to the first past last. So here we get +2. Now, let me compute prefix sums of this array, and you will see that prefix sums of these are exactly that. So -2 plus 1 is -1, -1 plus 0 is -1, -1 plus 2 is 1, 1 plus 0 is 1, 1 minus 1 is 0. Exactly the same array. So we are outsmarting our interviewer basically by not doing much work. We only do 2 updates. And updates in Fenwick tree cost log n operations. And if you think about 2 log n is much better than n operations, right? If n is 1,000,000, then 2 log n is 40. Just like that. So yeah. And if this operation continued, you just have the same invariant going on. At any moment, the entry at index A of the actual array is a prefix sum of our Fenwick tree from 0 to I inclusive. And this can be computed in log n operations. That's it. Yeah, you can verify analytically that this invariant persists. So you always have this kind of identity. If you have it now, then after next operation, you will also have it. And you definitely have it initially because your array is on zeros. Now, if your array is not zeros, then first thing you have to do is just compute prefix sums. Okay? So to have this invariant from the very beginning, you have to compute prefix sums. And initialize Fenwick tree with prefix sums instead of the actual array. Yeah, like this. But I believe that I changed initialize method here, so it does prefix sums internally. Right. So then things are very simple. We just read queries. So if we have range update, then we. Oh, I defined another interface. Okay, it's not a big deal. So this interface is just queries at index and increments at range by using standard operations, prefix sum and increment at index. So when we increment, then we do 2 increments plus delta, minus delta at positions left and first past right. So right plus 1. Just like that. Query at index simply returns prefix sum. I don't know. Because, I don't know. I thought that it's a good idea at the moment. Yeah, so just like that, you have your video lecture on Fenwick tree. Now, just to give you some side notes, I already mentioned that initialization of the Fenwick tree is possible in linear time. It is possible because of the same idea as here, we just need to compute prefix sums, and because every entry of the Fenwick tree is some segment sum, we can compute segment sum by taking difference to prefix sums. So that would be a linear complexity way to construct. the Fenwick tree. Also, obviously, you can do two-dimensional Fenwick tree, which will be in between one-dimensional and three-dimensional. What else can you do? There are several upgrades to Fenwick tree. And by the way, Fenwick tree is also sometimes called a bit indexed tree. Now, I don't really like that name because our indices are not really bits. They are actual indices. Yeah, I believe that plural of index is indices. Yeah, in case you were wondering what I was saying this entire time, I believe that the actual plural in British is indices. Maybe in American it's indexes, but I don't know, it sounds odd to me. Okay, so bit index tree. Some people even like to abbreviate it to bit. I completely don't understand this. But if you are comfortable with it, it's fine. It's fine. Use whatever works for you. I would like to really respect Peter Fenwick as one of the authors of the data structure. I think he is a cool guy. I believe he works somewhere in New Zealand, in case you are interested in it. Yeah, and I know there are several other video tutorials on Fenwick tree, but I believe that people mostly don't shortcode, and they also don't solve problems from Codeforces, unless you are reading a tutorial Codeforces, but I'm not sure that a lot of you are. So again, these problems are kind of competitive, not really, like they are pretty well known by today, let's say. In 7 years, like every student who repeatedly takes part in competitive programming competitions, yeah, competitive competitions, whatever, knows these problems. So, but not everyone interviewing for, let's say, job at Google knows about this. I'm pretty sure that some of my friends working at Microsoft did not know about Fenwick tree when they were applied to Microsoft, let's say. So if they were to have like this problem on the interviews, it would be a different story. And as you seen yesterday, you totally can be asked about Fenwick tree. Of course, if you know segment tree, you can rewrite segment tree, but I believe that for beginner and intermediate level, and our series is not all that much concerned with super hardcore problems. We'll be solving some hard problems for sure, but it won't be like all hard problems, okay? Because interviews are not all hard problems. You will also have something simple to start, and then things will get gradually more and more difficult. So yeah. Knowing about the Fenwick tree and using it when you are too lazy to write a segment tree, which is obviously not that simple to write. I mean, there are several tricks for iterative segment tree, which makes things look prettier and shorter. But yeah, I do not remember all that many problems on LeetCode about segment tree. In case you are interested in segment tree, I really don't think that we will be doing a video on it anytime soon, because it's a somewhat complicated data structure, especially if we start talking about two-dimensional segment trees. and compressed two-dimensional segment trees, this is not what you want to study until you're like until you work at Google, I believe. Yeah. So I believe that would be it for today. Let me know what you think in the comments. If you want me to cover some other data structure or maybe an algorithm, 100% comment on it. I go through the comments. I appreciate your time to write the comments. So yeah, I will adapt to what is the requested content. And I believe tomorrow, or if I have time, then definitely tomorrow, or otherwise like on Sunday, or maybe on Monday, which will be very unfortunate if you are in Eastern Asia. I mean, time difference is complicated for me. So I will try very hard to release the second episode, the real second episode about phone interviews on the weekend. On the weekends. Hope you enjoyed. Have a great day and see you next time. Bye.